Yo. What's up, what's up, what's up? Welcome back. Today we're working on trying to get like some sort of like 3D rendering working with OpenGL. So what we've been working on kind of recently is we've been working on this like stream intro screen, which hold on, let me find it. It's this guy. And he's got kind of a invalid time, so let me just fix that up a little bit. Let's pretend that we're starting stream in 5 minutes. We have like this little window that pops up and he says like, hey, I'm gonna be doing something today and here's when my stream starts. And it's got this like fun little animation. It's like kind of like coding theme because this is a coding stream, whatever. So we've been working on that, and what I was experimenting with yesterday was we set up this like alternative scene in Godot. It's like a little 3D screen with like a CRT on it, so like scrolling text, whatever. And I was like, that's like kind of fun. This isn't like really like what I would want it to look like in like a final version, but like it's kind of like, it's enough to give me kind of confidence that this is kind of something that would be interesting to look at, is like how would we render like a 3D scene and like do the stream intro on here, and you know, fully embracing our tendency to do everything ourselves and not use software that does things for us in a nice, easy way. It'd be kind of fun to, I think it'd be kind of fun to like figure out like, well, how would we do this like without a game engine, right? Let's just like use OpenGL manually, and you know, saying that OpenGL is the lowest level is kind of a lie, but like, you know, let's just say that we'll use OpenGL and try to draw this scene. That's kind of where we're headed. And so the first thing we need to do is we need to figure out like how the fuck do we like render something in OpenGL. So what we have here, this like this version of the intro screen, this is already using OpenGL, and he's like rendering fonts in 2D on this guy through like OpenGL's API. He's like generating bitmaps for each of these glyphs and then putting them on the screen. And so we've like already got something set up that like can like put stuff on screen. And so the question for today is, how do we do that in 3D? So I think where we're going to start is probably, we're going to start by like rendering anything with like in a 3D world. Let's start there. And then from there we can try to like maybe start like dealing with like perspective and animation and like importing complex geometry and stuff. But the first thing we need to do is like get anything working, right? Let's just see anything. So yeah, I think that's where we want to start. So I think what I'm going to do is I'm going to work like within this existing OpenGL application, because there's a lot of like OpenGL context and like helpers and stuff like that that like are already set up there. So it's just kind of like a nice starting point. We get to skip some of the like bullshit that comes with OpenGL. Yeah, so I think let's just do something. So let's like maybe see where we can like slot something like that in. So we have like our main function. He makes like an OpenGL window. He sets up some like default OpenGL parameters, and then he like draws some stuff on every iteration of the loop. So I guess the very like, we'll just kind of skip all of the stuff that we're doing right now, just temporarily. We'll kind of like comment all this out. I guess we're tracked in Git, so I can probably just like straight up delete it. Yeah, let's just delete all of this and we'll replace our main loop with something else. So this is like our like normal draw loop where we just say like, for every frame, hold on, let me like delete all of this. There's a lot of stuff that like we're like initializing that we don't actually care about now if we're not doing that screen. Okay, so we like initialize and we just have like this main loop that says like, while the window is open, like clear the screen and then do something. So if I cargo run now, I should see, yeah, just nothing happened. We just clear the screen, make it gray, call it a day. And so the question is like, how do we draw something? So I think probably something easy to start with is a cube. So sorry. OpenGL is kind of like structured in a way where I think like the minimal working thing is to give it two what they call like shaders, which are just like programs, code that runs on the GPU. And so if we want to draw a cube, we're going to draw like a bunch of triangles. So we can imagine that this is our cube, like this. So we have a point here, point here, point here, and then a point here in the back. Right, so this is like a cube. And what we do is we feed each vertex, each like point, each corner, I guess we can call them. We feed these to the GPU, and if we draw like, if we send like 3 in a row, we can say like, draw this triangle, please. And so what we do when we want to draw, if we want to draw a cube, is we kind of specify like, hey, I want to draw like, I'm gonna like pass you these vertices in like a specific order. I'll pass you like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then like if once I send all of them, then the GPU can draw them and we should get our cube. So I think the first thing we want to do is like figure out like how to set that up. So let's kind of make like a cube renderer, I guess. So we'll say like cube renderer. And we'll say he is a cube renderer, and he's gonna have like some like associated state with him. And he's going to do something like, he's gonna have like a way to create himself. Renderer. And he's gonna have like a way to render, right for now. And I'm just clarifying now, in case somebody is in here who actually knows what they're doing, or like knows some more than me about this. Generally, you wouldn't do it this way in like a real game engine. In a real game engine, you would kind of like batch all of your renders together. But for now, we're just going to say like, okay, I'm going to call render. It's going to draw to the screen right now, because that's just like an easier way to think about it for the time being. We have to include this guy, so we'll just say mod cube renderer. And we have these like 2D renderers that we've kind of worked with before that'll give us like some sort of structure to work with. So these guys like allocate some buffers that are like the vertex data that you upload, like each of these guys. These guys have like a point in space that they're associated with. And so you need to like give those to the GPU to say where they are. Because you could draw anything this way, right? You could draw a triangle. You could draw like, I don't know, like a 3D, well, like whatever. It doesn't care about like cubes. It just knows like, I'm going to give you points. So somebody has to tell it what points to use. So that's these guys. You have like a shader program. So if you look at like a vertex shader, what comes in is like you pass in for each vertex. This will run for each point. And it has like inputs associated with each point. So in our 2D version, it was like a 2D representation of a point on screen, as well as like some like texturing data associated with it. Then we like do a little bit of math to like move that guy around, and then the OpenGL takes care of like the rest through the fragment shader. So in our 3D version, we're probably going to have like a program that runs that vertex shader. So we're gonna like keep track of that guy. We're going to have the same concept of keeping track of our inputs through like the buffer is like it's like just kind of like the raw data. So if I like had each point here, I might say like my buffer might look like, 0, 1 for like one vertex, or I guess in 3D we might have like one point is at like 0, 0, 0, and the next point is at 1, 1, 1, right? So like X, Y, Z, these are like the coordinates on each axis. And if you were to like pass this in, the buffer would say like, hey, this is just the data, like raw passed in as like a flat array. And then the vertex array kind of says like, okay, here's how I'm going to chunk that data up and pass it to the vertex shader. So the vertex array is kind of like responsible for grouping, and the buffer is just like, here's my data. So we're going to keep up those guys. And we need a reference to the OpenGL context. This is just like a kind of Rust-ism. The like library that we're using to do OpenGL stuff in Rust, he kind of has like a handle associated with him, so we need to pass him around. Let's include some extra stuff here. So we have native buffer and native vertex array. And we have to like create these guys. So What do we do here? Here we, in our 2D version, we like compile a program. So we're gonna have to like figure out what this program is gonna look like. So we're gonna make a new vertex shader probably for 3D. It's gonna call, we're gonna say like what 3D vertex for now. We'll figure out later what that actually means, and then we'll make a new fragment shader as for now as well. But we likely won't need that. There's a good chance that like we can reuse our 2D fragment shaders for 3D because we haven't really got there. But the fragment shader is responsible for like coloring in a particular face. So if I'm like drawing like this triangle here, like with these 3 points, the fragment shader gets run for like every pixel is visible essentially. So hand wavy. So he's gonna like run here, here, right? Imagine like this is like a low resolution thing. He's gonna get run for each point on here. And so like in our 2D version, what we did was we just like, instead of rendering a like thing in 3D like this, we kind of like pretended our 2D world was in 3D. And like if you were to imagine just drawing like a square and then that happens to fill up the whole screen, then our fragment shader gets run for like the full screen. And so like theoretically there shouldn't be any difference between running a fragment shader on this triangle and running a fragment shader on this plane. Even if they're like warped in 3D, it shouldn't matter. But for now we'll like make a new fragment shader because they might have like different associated inputs or something. Who knows? This guy's gonna have to take in a reference to the OpenGL context. So we're just gonna smack that guy in here. He needs some like lifetime shit, so we'll just kind of shove that on here. Okay, and he's unimplemented, and we need to make those 3D vertex and fragment shader files, or else Rust, when it tries to use them, will be like, I don't know where those are. So we get edit source glsl, and we'll just make 3D vertex.glsl, and we'll make source glsl 3D fragment.glsl. And now this should compile. We just need to use our create gl util stuff. And we'll smack all this in an unsafe block. Okay, so I think this compiles again. It won't run very well. Well, I guess it will run right now because we don't try to actually compile or use the cube render at all, but we should. So let's go into our main function, or wherever the fuck we were, and we'll just kind of say like, somewhere we need to like create our cube renderer. So we'll say let cube renderer is equal to cube renderer new, passing in our GL context. We need to use that guy, so we'll just say use cube renderer renderer. Okay, we need to make him public for Rust to be happy here, so we just shove a little pubs on here. And then every iteration of our loop, we should just say cube renderer render. Bing, bang, boom. Okay, so hopefully we crash here because we tried to construct this guy and he won't finish constructing. But if we compile, we know we're on the right track. And I like to kind of keep us compiling as we move because it makes things like the like tooling around Rust will work a lot better if I'm compiling correctly instead of just like fucking trying to like parse my whole file with like the wrong like brackets and shit. So and it also helps with like lifetime management as well, like making sure that like my mutability and lifetime is in the right state from the get-go instead of trying to patch it up later. Okay, so let's see, we have our program. We need to put stuff in those shaders and we'll figure that out later. We need to go back to our 2D renderer and like kind of look at what they do. So they create a vertex array. So this is what we were talking about this handles like groupings. So we need to allocate one of those guys. And then we bind him to say like, hey, OpenGL, you're very stateful. I have this vertex array. Please, when I like update attributes about the vertex arrays, make sure that you're using this guy. So that's what this like bind is doing. Then we have to generate a cube. We'll have to generate a buffer that represents a cube, which we don't have. We don't know what that's going to look like yet, but we'll figure that out. So we'll have here a function that's like generates cube buffer, and this guy will take in an OpenGL context, glow context, and he's going to return a native buffer. Let's just move this guy a little bit out of the way. So he's going to return a native buffer. Okay. And so he will say he's unimplemented for now. And then here, when we try to like create him, we say instead of generating square, we say generate cube. And here we're missing some like context stuff we need. So I think glow needs to pull in like a trait has context for all these functions to resolve. Nice. And then we also here allocating things can fail. So we need to import an error type and return a result here. So here we'll say we can return a GL error. Okay. Okay, which means that we need to use create GL error. All right. In our main now, since we returned a result, this guy needs to be unwrapped into his correct inner child. Okay, so we have our program, we have our array, we have our buffer. I guess technically we don't have to bind these guys right now because we're not actually doing anything with them, so we'll just kind of keep those there for reference, but not use them. And then here, we should have enough to say, please return our cube renderer, who has a program, a vertex array object, and a vertex buffer object. And a handle to GL. And then go like this. And we say, you succeeded. Okay. We are okay doke. Okay, so now when we run, we crash because this program that we're compiling isn't like a valid vertex shader. So let's maybe try to figure out what like a vertex shader for 3D would look like. So we can like reference one like our other ones that we were using before, and we start by saying like, hey, you have a GLSL version attached to you, so we'll write that at the top so that you know what APIs are supposedly supported. I think there's other things. There's probably some other semantics in there, but I don't really know what they are. Well, let's figure out what our inputs are going to be. So for each vertex, for now, let's just say that the only thing that we take in is a 3D point, and we'll figure out what that means later, like what we're going to do with that. And maybe for now, we can take in that 3D point in screen space. So something important to think about when we're working with OpenGL. OpenGL kind of views the whole world as a cube. So you can imagine like this is like the OpenGL world. He's like in this cube. And everything you draw in this cube will just end up on the screen, but kind of like wherever you put it, I guess. Here, hold on. So let me draw this a little bit better. So I think this corner kind of like looks like it should go like here. Yeah, that looks a little. It's still kind of warped, but whatever. So imagine like I draw like kind of like maybe like halfway down the cube, like the OpenGL world. I just draw like a little smiley face here. And then maybe in front of it, oh, smiley face is kind of bad. We'll say we just draw like a square here. And then we'll draw like another square in front and to the left here. So you can kind of imagine like my eyeball is like looking through this cube like this. And like what that will render on the screen like is like the square on the left and the square on the right. And like if the square on the right ends up like a little bit behind, then like we would see maybe something like this. There's no like perspective built into this. So if I draw like two squares that are the same size, right? Like they're both this large, but then I draw the second one like up here. Like even it should, if it's closer to us, we should see it be bigger. But what we would see is actually like, we wouldn't be able to tell, right? We would just see two squares next to each other, no matter like how deep this guy goes into the screen. So that's something to keep in mind. And when we're dealing with perspective, we end up just kind of like warping the whole world to look like we would see it. But we'll handle that in a minute. So all I'm saying this for is maybe right now we will take in our vertices in this world, right? So we'll to draw our cube, we could maybe like put points in this world in these locations, and then we could draw a cube based off of that. So we'll just say that our vertex will just take the thing that comes in, and we will set our position to that value. So we won't do any scaling or anything. We'll just say use the vertex as you see it. So we can say invert, and GL position, I guess, is using this like 4-dimensional coordinate, which is kind of odd. Let me just double check that. Let's just double check. And so this is like a kind of like intrinsic output of the shader. Like if we know that like when we assign this value, OpenGL will like take that and do something with it down the line. Let me just double check before I say the next thing that I understand this correctly. So they're using vec4 GL position, and I assume, I could be wrong here, but I assume that this is like they're building into OpenGL this thing called like a homogeneous coordinate. Which is kind of, is this Wikipedia article going to say what I mean? In computer graphics and vision, perspective projection versus blah, blah, blah. Okay. I don't remember like what the right keywords are to Google this, but it essentially means that like, if I remember correctly, or if I understand this correctly, if you have like X, Y, Z, and then like some number, 1.0, basically what happens is the point in 3D space is these three numbers all divided by this. So this should turn, like if this was like 2, then this would turn into X over 2, Y over 2, Z over 2, and that's like what would get drawn. And there's like some like very useful reasons for that. Like the math just kind of works out very nicely when we start chaining this with other stuff. But for now, we'll just like, we'll say we are going to use this as like a 4-dimensional vector where the last element is set to 1, so we don't have to, like, it basically is like a no-op. Okay. So now we need like a vertex or a fragment shader to go with it to color in whatever we're drawing. And so here we can say set our 3D fragment shader, and we can just copy one of our other ones, which we have here. And this guy is just going to take in nothing. He has no inputs. Great. He has a color output, and we just set the output color to white. So we should see a white cube once we're all done with this. So let's check that out. Main panicked at not implemented. Okay. So we're probably panicking at this like not implemented generating cube. So we're going to need to draw, we're going to like break up our cube into triangles. And I guess, how do we want to do this? We're going to make like some floating point numbers that represent each corner of the cube. Yeah, seems reasonable. I guess maybe we'll draw a square first so that we have to think about less vertices, or maybe even a triangle first. Fuck it, we'll start with a triangle. Just to make sure that we have like the inputs and outputs of our shader correct. So our triangle will start with, we'll say let data is equal to, going to be a slice of floating point numbers, and he's going to just have 3 points on him for now. And we'll kind of build up from that as we go. That way we'll have like some sort of like intermediate thing to look at to make sure that we're getting it right. So the first thing we're going to be at like maybe 0.5, 0.5, 0, right? This is like X, Y, Z. Maybe this should be like X, maybe my Y, if this is like the top vertex, should be a little bit higher. Then we're going to have maybe the bottom left thing at like 0.25, 0.75 or something. And the bottom right at 0.75, 0.75. So that should be something like this, right? If this is our screen, we should be seeing like this. And this should be white. So then we need to like pack this into like a buffer for OpenGL. So if I remember correctly, we have a utility function somewhere to help us with that. Where would we have been doing this before? We would have been saying like buffer data to U8 slice. Nice. Yeah, okay. So like a little like aside about like the API here. This is like data that is like floating point numbers, but like the OpenGL API kind of takes in everything as like U8 buffers and then casts them back to whatever they should be later. So we're gonna have to like reinterpret this guy as a bunch of bytes, pass that to OpenGL and tell it to cast it back. Which, let's see, what does that look like? We have to create we create our buffer. This is like the OpenGL representation of the data. We say, please, when we do buffer actions now, please associate them with the buffer we just created. We return that buffer. And now we just need to put the data in. So that's this function here, where we say buffer data U8 slice. And I guess we're going to have to convert our floating point array to a bunch of bytes. So I think we can just do like 32-bit float to U8 slice, and this will take in a bunch of floating to point numbers. And we just say, hey, I'm gonna like convert this thing into a pointer, cast it to a U8 pointer, and then make a slice from that thing. And that should be enough for OpenGL or our like Rust API to work okay. We'll pass in the data here. Cool. And then I guess we probably have our triangle. We'll have a triangle here. So then we have to kind of like associate the right things with that, right? We have to say like, okay, so we have this data, but we need to tell OpenGL what that data is, right? Because in our vertex shader, we have this 3D vertex. We say, hey, each thing is going to be like a 3D vector, but you could have like many of these things, and you need to say like where in the buffer those things are packed, essentially. So after we generate the buffer, we have to assign those packings, which, nice. It's kind of done like this. So we'll bind our array. I guess binding the buffer may or may not matter. It doesn't, we're not really sure. I'm not really sure. And here we kind of say, here are some attributes. So let's look up GL vertex attrib pointer. And here we say, here is the index that we're modifying. So like which input, essentially. This says, how many elements are there? So we are going to have 3 elements per vertex. This is going to say like what type should you cast this stuff back to? So here we say float. Here it says should they be normalized or interpreted as directly as fixed point values? I think we do not want any normalization. How many bytes are between each attribute? So this is going to be we have 3 things times the size of a float. So we say float 32. And then we have where is the first component relative to the start? So this is just a 0 for us. And here we can say, well, maybe like make a variable stride here, which is an I32 because that's what the OpenGL API expects. And we'll say this is this guy, but cast to an I32. So we'll say try into and expect size did not fit in I32. And we can just use this here directly. And he can't be a constant actually for some reason because try into is not a constant, which is kind of fucking annoying. So I would have liked some sort of like compile time. Maybe we could do like a compile time guarantee here. I don't know if Rust has like static assertions. Or like static try into. I guess maybe we could like wrap that in a function. Can you like compile time try into Rust? Yeah, we can do something like this probably. Const function, like stride. And you could say like 3 times this. If I do this like in a const function, I think that will compile. No, it does not. Fuck. Okay. Well, I'll just write as I32 for now. Fuck it. But I would like to have a better guarantee there. I guess you could like assert that the size of this thing as a U size is less than the 32-bit integer. You could like manually assert that first, but I don't want to. Yeah, fuck it. We'll say const stride. Yeah, well, whatever. Fuck it. We'll deal with that in the future, or we won't. I'll just ignore it. This guy's saying enable that input, and in reality, I think that we should like look up the name of our input before doing this. So I think there's like a named version of these APIs that says like I want to go by name essentially. So what's that called? Vertex GL named vertex attrib pointer or something. Or I guess we get the location by looking up the name. The first argument gets yeah. We like find the index. Received from calls to GL get attrib location. That's what I'm looking for. So we say GL get attrib location for this program that we compiled, and the name of it is something. What is the name? What did we name it? We named it oops. Wrong button again. Fuck. We named it 3D vertex shader. We're looking for invert. So say vert location is this, and then we can pass that as the first argument. And expect here no invert. All right. So all of that, just to like kind of say to OpenGL, here are where my vertices are. And so now we should be able to like when we render, let's reference the 2D version that we had. So glyph renderer. When we render, we use the program. We use our vertex array. This. We'll drop this on an unsafe block for now. This just says like use the parameters we set up before. And then in this version we were like substituting data. We're not going to do that right now, but we do probably need to bind the buffer, I assume. I'm not sure if binding the vertex array automatically binds the buffer that it was associated with before. I'm actually kind of curious about that. GL bind vertex array. Let's see. He binds the array. If no vertex array is object, blah, 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 it's none is bound. Does binding vertex array automatically bind buffer? Let's see. Do VAOs also automatically bind indice arrays? Okay, this is kind of what I'm looking for. A VAO does store the element array buffer, so it probably also stores the buffer as like there's element buffers and array buffers. I think we can probably assume that those are the same, automatically bound. So here, as long as before we unbind our VAO, so we can say like, hey, bind vertex array. We're done with this. So like any other actions that we take aren't associated here. And if somebody else tries to do buffer data manipulation later, they won't have to, like, they won't affect us, I think. But we'll see. We'll see. Okay. So all of that to say, we now have, like, we're back in the state we expect to be when we used to call this render call. Normally you would probably try to batch these. You would say, like, everybody who's using the same program, like, we'll only do this use program thing once, but we're just going to do it here for now. In our 2D version, we were like doing like some like texture stuff that we don't have to worry about, some like input parameter stuff we don't have to worry about. And then all we do is draw our triangle. And then we can unbind these things so that nobody else will affect us after our render call. I think triangle strip it doesn't really matter. What are the parameters to GL draw arrays? The parameters are first, so like which element do we want to draw and how many do we want to draw? Because you might have like multiple different things kind of like packed into the same guy, and so we're the same like buffer, and so here like we could draw a subset of him, but we're not going to. So we're going to draw one triangle of 3 vertices. And what are like options for mode? We'll draw them as triangles, not triangle strip, like this. And I think that we might actually see it. Nice. We do see a triangle there. That's pretty sick. Now we made a silly mistake here of assuming that the coordinate system is 0 to 1. But the coordinate system here is actually -1 to 1. So if we want this to be centered, it has to be centered around 0. So here we could just do anywhere we had 0.5 here. This should be like this should be 0 instead of 0.5. This 0.25 should be like -0.5, and any 7.5 should be +0.5, I think. And that should, there we go. So we see this triangle stretched out. Note that like this window that I can't resize it because that's not hooked up, but like the top, like no matter what the aspect ratio of this window is, we're still gonna have like the same mapping. So in like our main function, if we go back over here and we change our window from like a 16 by 9 to like 1 by 1, right? We see like the triangle just gets stretched with the window. And so we'll have to probably account for that later. But for now, I'm not going to. Okay, so that's our triangle. And so I guess maybe the first thing that we can do is let's make 2 triangles, but make one kind of close. So we'll put this one at like, if the Z direction is -1 to 1. I don't know which one's bigger and which one's smaller. Maybe we could define that. We probably do. But let's do like the same triangle, but maybe put them like side by side. So instead of taking up like the full screen, maybe we'll draw one in like the top corner and one in the bottom corner or something. And that way we'll be able to like put one deeper into the screen and maybe try to figure out how we should like make one look farther away from the other. Yeah, let's do that. So how do I want to handle that? Maybe we'll put like one here, one on the left side of the screen and one on the right side of the screen. Which just means that this guy is going to have his X coordinates all in the negative. So this -0.5 is going to become -0.75. And the +0.5 is going to become -0.25. And then on the other side, we're going to do the same thing, except the negative thing is going to be, this is going to be 0.25, and this is going to be 0.75. Oh, wait, I only wanted to do that to the X coordinates. Fuck. So it's actually, yeah, so x coordinates are all I want to modify. And so the center thing is going to be negative 0.5. The left is going to be negative 0.75. And the right is going to be negative 0.25. And then on the right side, the top is going to be at 0.5. The left is going to be at 0.25. And the right is going to be at 0.75. Okay, so we have one triangle. And now let's say that we want to draw 2 triangles instead of 1. Which means just draw 6 of our vertices. And now we should see 2. Great. And let's maybe color them with their distance from the camera. With their like depth in our OpenGL world. And then we can use that information to confirm that like one that is a darker color should be farther away or something, or brighter should be farther. So let's draw the first guy, maybe at like the left one we'll draw close, and we'll assume that positive z is farther. I don't know if that's going to be true, but we'll figure that out. So yeah, we'll say positive z is farther. And so here we will say that this guy's at like 0.5. So like 3/4 of the way in the world, and this guy's going to be at negative 0.5. And so what we should see is we still see no change, but we'll deal with that in a second. And our fragment shader for 3D, let's say he's going to take in a float that is his depth. And he's just going to use this guy. His output color is going to be the depth and full alpha, very visible. And that means our 3D vertex shader has to output a float at some depth. And we'll just put our depth is equal to our invert z position. Okay, so now we see one that's really dark and one that's gray. We should probably normalize this guy. So we'll just say that our, we'll put this in the range of 0 to 1 so that he's like a color that we can interpret reasonably. So if this is negative 1 to 1, we need to add 1 and divide by 2. There we go. Okay, so we have one that's close, one that's far, and we want to see these guys scaled. So what does that mean? Okay, so how do we explain this? So if I'm here, we're like looking from the top down. This is me. I'm a little dot. And say there's like a guy lying on the ground here. There's like a dude lying on the ground. And the same guy is lying on the ground here. From my perspective, this guy's going to look a lot bigger, even though like they're exactly the same person. And so you can kind of imagine that I have like a field of view, right? So we'll just draw a triangle coming out from like my eyeball. And if you were to like draw this guy as like a percentage of my field of view, this guy would look very big and this guy would look kind of small, right? Because this guy's only taking up like, what was this, like a third of my field of view, and this guy's taking up like maybe like over half of him, right? Even though they're the same size. And so what we can do, if our OpenGL world is like a cube, is we could kind of like define the closest thing that we're going to draw and the farthest thing that we're going to draw and warp this to fit that. So we could like take this guy and convert him into like a completely like aligned square with like perfect sides. And we would just stretch this guy so that he takes up, you know, the full like this area. But this guy, he's only taking up like a small amount. So he would still kind of like show up over here like this. If that makes sense, like we're kind of like warping everything. We're stretching the stuff that's close and we're like compressing the things that are far, essentially. And so you can do that with like a little bit of trig, I think, right? So we know the distance that this guy is to our camera. and we know, right? So we can say that like we'll use like our coordinate system that we were using before, where like negative. We'll just say that this is -1 and this is 1. And so we can say like for each point on this guy, scale him relative to his distance. So what does that mean? Let's think. I guess we do have to. This will probably be easier if we define some sort of world. Let me think. Yeah, because we kind of need like a point in the world that we consider our eyeball, and then we position these guys in the world relative to our eyeball, right? And we can also define our field of view, right? Like how much things are stretched will kind of be relative to this angle, right? Because like if our field of view was like wider, the whole world appears smaller, and if our field of view is narrower, the whole world appears bigger. So we're gonna need. I guess we'll say that we're working on perspective now. Perspective. And so what are we gonna need? We're gonna need. We'll go back to our 3D cube renderer, and we're gonna need some things. We're gonna need our field of view. Where in the world is our eyeball? And also, like, which way are we looking? Those are all gonna be important here. And so, like, we need to figure out what are we gonna, like, define our triangles as. We can define them as sitting in the same spots. And we'll say in our naive world, where we had like these guys drawn at -1 to 1, we'll just say that our eyeballs are at like -2. So eyeball at -2.0. And so like now we need to do some math to figure out. I guess we'll like hard code our eyeball field of view as something. What's like a reasonable field of view? In video games, I see things from like 75 degrees to like 110 degrees. 110 looks like pretty fucked up and warped. So let's say that like our field of view is 90 for now. That should be somewhat reasonable. And so then we can say for each vertex, so let's say we're drawing this guy's foot. We have a straight line to his depth from us, how far he is along our z-axis. And we have his like x position, we'll say. We'll ignore y for now. And so this makes like a triangle. And where he gets mapped on this plane, the closest thing we see, I guess that doesn't really matter. All we have to do is kind of stretch him according to this. So we need to figure out where he is as a percentage of this triangle, right? So we have this guy, green triangle, which is like the vertex position, and then like yellow triangle, which is the edge of our screen. And then we just figure out where he is as a ratio of that. So I guess that probably maps to like, if we find, if I remember, like, let me think, sorry. I don't know if this is going to work out to be just like angle percentage, but we can probably figure that out. So let's say our field of view is 90. That means that this yellow angle is going to be 45 degrees. Z is constant for both. So we have opposite over adjacent is going to be tan 45 if our field of view is 90 equals x over z, where x is like x is our field of our width here, then this guy is going to, fuck. Maybe we use like big X and Z here. And we'll use little x to define his x coordinate. So his x coordinate is like 10 something is going to be his small x over z. And then we want to find like the ratio of his x over big X. Which is, I guess we don't know the angle yet, but we can figure it out from these guys. I know that this math is doable. I think that this might just end up scaling with distance. Because everything along this line, will have the same position. I know that we can derive this. I know it's possible. So I guess we can find our big X because we know our Z. So we'll say that like big X is Z tan 45, right? Is equal to X. And so if we're looking for his x position relative to that, that's going to be like x over x, which is going to be x over z tan FOV. Yeah, that seems reasonable. So this is like a constant. That seems right. Okay, so we'll just take each position, each vertex position, and divide him by his depth and some like constant for our perspective. That seems reasonable. Okay, so tan FOV is equal to 90 10. Not a number. Sick. I should have seen that coming. So we shouldn't express it this way. We should not express it this way. I guess we could just, for now, pick a smaller number. But we'll have to figure this out at some point. So we'll just say our FOV is 80 degrees while we figure this out. Oopsies, we were looking at the cube renderer. So tan FOV is 80 tan, so like 5.67. Sure. Oh, oops, no, because we have to half our FOV. Shit. Okay, so if our FOV is 90, we need to do FOV over 2 here. Yeah. So we have 45, tan is 1. Sick. Okay, so that lines up nice. So tan FOV over 2 is equal to 1, which means that our perspective mapping is just x over z. So we move everything in the world to be x over z. Yeah. So closer things. This is a distance from the camera. Okay, so closer things will have a smaller divisor, which will make them look bigger. That seems right. Yeah, that seems right. We could try that. Okay, so in our vertexator, let's just, for now, we just divide everything by z. but not z. We need to divide it by the distance to the camera. So let's just say for now, our camera's always going to be facing forward z completely, just to simplify things for now. But we will have to set our camera position. So right now we'll just kind of hard code that. Can you do constants in GLSL? That seems reasonable. Uniform or constant is probably negligible. Oh, yeah, if I remember correctly, const float is perfectly valid. Nice. Okay, so we'll say, for now, the constant, the float of, what were we trying to say? The camera position on the z-axis. We're going to put him at negative 1.0 for now. And so that seems reasonable. Then we're going to find the distance in z to each vertex. So we'll say float z distance is equal to camera position z, and the position of the thing minus our position, right? So we'll have like the invert z minus our position. And then we just divide his x and y by his z. So we'll say float out, no, vec3 out vert is equal to invert.xyz, or sorry, just invert. We can't modify the input if I remember correctly. So I reassign them. We say outvert.xy is divided by our z distance. And then I think everything else just kind of works out, I think. So that didn't do jack shit. Can we set our depth to z distance, just to see? So that did jack shit. I would have expected something more. Maybe the distances are too small for it to matter. So maybe we can like crank up the z, like pretend that our field of view is extremely wide or extremely narrow to like magnify the difference. What if, okay, let's just say we divide by z distance times like 1,000 just to like try to see if we can like amplify the effect. Which we don't see, which is very odd. Let's think. How can we debug this? Because I would have expected a very large difference there. It would be interesting to render our X, Y, Z as the color, which might give us some sort of clue. Are you still using invert in GL position? You need to use, oh, thank you. You are attentive, and I am an idiot. Thank you. There we go. Okay, so that's what we expect to see, right? Our triangle on the right got a lot bigger and closer, and in fact, he moved so close that we like didn't render the whole thing. And the small one got a lot, he kind of stayed approximately the same size. He got a little smaller, I think. Pretty sweet. Okay. So that's perspective. We should probably be able to like adjust the position of our camera. So we'll set him as a uniform. And let's try like adjusting his position at runtime here. So we basically say, hey, we have some uniform that we want to modify before we do any drawing. And we need to like figure out where that uniform is, which means that we need to like look up his uniform location, which is going to be something like this. We're going to say, before we render anything, we're going to request the camera position location, and we're gonna pull him from the program. We're gonna say camera pause Z, and we're gonna save that guy so we can reference him later. And he is like some like fucked up complex type. Glow context as has context uniform location. Great. So we save that guy. And when we now set this guy, we should be able to say, hey, use our camera position location, and let's set it to like negative 4.0. And then if we do that, hopefully we should see, yeah, we see the two triangles at different sizes, and if we move the camera closer, maybe negative 2.0, they get a little bigger, and we move them even closer, and they get even bigger. Pretty sick. Pretty sick. And maybe if we really wanted to get crazy, we could animate. We could maybe like animate the movement of the camera to like in and out relative to the triangles. So we could maybe on render take in the camera pause as an F32, and we'll set this to camera pause. And on each frame, we will like bounce the camera back and forth essentially. So we can say like, let camera pause equal to negative 1.0. And on each frame, we'll take like a delta from the last frame and move him by some amount relative to that. So we'll say let now is equal to instant now. Let time since last is equal to instant now minus last frame time. So we'll actually call this last frame. And then we'll update this guy to say last frame is equal to now, I guess. And we do that at the end of the loop. And then we say now is now, and time since last is equal to now minus last frame. Cool. Then we say update the position of the camera to be like, I guess we'll just increase his position with time or decrease his position with time. So we'll say camera pause minus equals time since last as seconds in floating point. And then we can just set the camera pause like this. And we set it to mutable. And what we should see is the camera like drifting away. Oh, baby. Look at that. Isn't that sick? That's pretty sick. That's pretty sick. Yeah, that's cool. That's cool. Okay. Okay. So, I guess we need to start building up this idea of like the next thing to build up would be rotation, probably, right? We might want to render something not completely aligned with the camera. So maybe we'll upgrade our triangles to cubes and then try to animate rotation of a cube, right? That will give us something to look at, and that will allow us to start like manipulating things in 3D space. Okay, so the next thing is we're gonna say at maybe like an hour in, the next thing that we're gonna work on is rendering, rotating. We'll say rendering any cube, and then at some point in the future, we'll try to render a rotating cube. Okay. Cool. So we can go back into like our 3D renderer, which we called cube renderer, a little aggressively, because we thought we would start with cubes. And let's do the same thing that we're doing now. And let's say we have 2 cubes. Well, we can start with 1. We know that we have like our like depth perspectiveness working. So let's define a cube. And we'll define him in that like box that we were talking about before. That's like kind of like the OpenGL world. So we'll say that he is. I guess that's kind of not true anymore. Just to clarify. So before we were kind of saying that like the whole OpenGL world lives in this like 3D box, right? Everything you draw in this box will show up as if you're looking through this and there's no perspective. And essentially what we've just done by implementing perspective is we've kind of done this where like we have like our eyeballs are back here at like one like location. Like maybe it helps if I draw more here. But they're kind of like looking forward through this hole. And we've kind of like expanded the back and shrunk the front of this cube so that like it looks kind of more like this now. Where like the angle of our field of view determines like how these corners are mapped, if that makes sense. And so like the things that we were drawing inside before, if we tried to draw a cube at like, if we just like put a cube in this box, the cube would now actually get warped with the box as a whole, if that makes sense, like according to these angles. So if we try to define a cube and we say like, we're going to put his front vertex, let's just put him at like negative point, we'll put him like halfway in our like area of visibility, I guess. Also called the view frustum, if you're Googling this later. OpenGL frustum. Frustum. I don't know what the fuck is a frustum? Where does this word come from? I just want like definition. In geometry, a frustum is a portion of a solid that lies between two parallel planes. Okay, so we have the front plane and the back front plane and the back plane, and between them we've created a frustum of stuff that you can see. Okay. Hello, why is there a maze thing? Very reasonable question. Otherwise, you know, people might get bored, right? So there's just a thing in the corner for you to look at if you need something to look at. I heard about like this thing on TikTok that's called like overstimulation videos. Yeah, I've Googled this before. Where essentially like people browse, you know, you have like TikToks that are like really fucking short and like punchy content, and people are desensitized to that amount of like stuff entering their brain, and so people will put like 4 videos on at the same time in this like 30-second video, and so this is essentially trying to like capture the same part of your brain that whatever like those things do. So like a video with GTA racing at the bottom, yeah, like fuck it, why not? Just so that you know, sometimes people like to look at things while they listen to something else. Can you change the maze screensaver to the pipes instead? I'm desensitized to the maze now. That's actually a good point. I did notice that when I was like rewatching my streams initially, I would like just kind of stare at the maze a lot. But I don't even notice it anymore. So you're right. If I want to keep the same people engaged for longer, I actually do need to go back and re-implement a different screensaver from Windows 95. So maybe we'll do that at some point too. Maybe we can do that after we figured out 3D rendering in OpenGL, right? And then that will make that we can do it with our own engine, which would be kind of fun. Okay, sorry, distracted. I wanted to draw a cube. So let's define, maybe first we'll draw a square, and then we'll draw one face of the cube, and then try to like tack on faces so we can see like some sort of like iterative improvement. So we'll start with like the front face of it. We've become so desensitized to content, we now need 2 pieces of content to stay engaged. And we're kind of saying now that 2 pieces isn't enough, even. We need like maybe 3 or 4. Maybe we'll expand over time so that the whole stream is just covered in shit. And you won't even be able to see what we're doing. Because what we're doing is programming. Programming is boring. So, you know. Okay, let's draw a square. So you could think of a square as 2 triangles that are connected to each other. So we'll just draw like these two triangles like this. And we'll draw them as like quarters of our screen essentially. So this is negative 0.5, this is positive 0.5, and same on y-axis. So one vertex is going to be at negative 0.5, negative 0.5, and we'll put him at some z location. Let's start at negative 0.5 for now. And we're going to start with like one triangle that goes these three here. 1, 2, 3. So the second vertex is going to be positive, positive. And the third one is going to be negative, positive. Just for the record, this whole y-axis might be flipped. I can't remember. I think it's probably 0, 0 is down here, and 1, 1 is up here. Negative 1, not 0, 0. But it doesn't really matter. We'll get the same shit either way. And so let's first draw, I guess we'll draw that triangle first. So we need to draw three things at this point. Yeah, okay, so we see our one triangle there, great. And it is upside down, which is fine, doesn't really fucking matter. And we'll just draw another triangle exactly next to it. So we're gonna have the same top left, same bottom right, but now our top right is gonna be positive, positive. So now we should see a square. Nope, I fucked that up because we are only drawing one of the two faces. So we need to draw 6 vertices now instead of 3. Still no bueno. What have I missed? Negative, negative. Positive, positive. Oh, these are the same vertex. I'm an idiot. This should be positive, negative to flip this guy. There we go. Okay, so now we have a square, and he's getting pushed into the distance. And now let's try to stick another square, but now we want it to be on the side or the top or something. Now, I wonder if this is going to get a little fucked up, because like if we put the other square behind, like any side that we do, I don't know if we're going to like see it, because we're looking straight on, right? How many fucking paint windows do I have? Let's close them all and start. Oh, geez, that was loud. Ow. Ow. Okay. So the problem here is that, say this is the box that we're looking at, right? And we draw a cube in here. Womp, 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 womp. Right? Basically, like so I'm basically back here. Here's my eyeball. If I draw lines, like kind of where I can see relative to the cube, because we're looking straight on, we're actually never going to see anything but the front face, right? Because these vertexes back here are kind of like stuck behind the front. So we need to find a way to visualize our 3D object without this problem. So maybe it actually makes sense, before rendering a cube, maybe we start with our plane and we rotate our plane. And once we've rotated our plane, then we can add on other faces and we'll see them. I think that seems pretty reasonable, actually. So we'll start with just the front face and we'll try to build up this idea of rotation. Okay, so I watched this video at some point that like kind of unlocked this concept for me. In a way I've never, I'd worked with these like transformations, they call them, before, and I didn't really get it. But okay, hear me out. Say you're in 2D. We're gonna ignore the third dimension for now, because doing that just makes everything easier. I have a point here. This is like some point x, y. And say I want to rotate him around the center here, right? You can kind of like rotate him like this by some angle. And if you imagine, instead of him rotating around the center like this, you could imagine the whole world rotating. So it's actually easier to draw that. It's easier to show this if we draw him on an axis. So say he's on the axis at position like x1, y0. And we want to rotate him by 45 degrees. You could imagine that as rotating the whole set of axes 45 degrees. So we would end up with like these other set of axes like this. And he would still be at 1, 0 in this from like the perspective of orange. But if we want to see like what that change is from our perspective, right? We now have some new x, some new y, that we know rotated by like 45 degrees here. And so his position in x, we know that like this distance has stayed the same. So we can use like a little bit of like high school trig to figure out his new position, right? So his new x position is going to be cosine theta, right? Because that's adjacent over hypotenuse. And his new y position is going to be sine theta, right? Because that's the opposite over hypotenuse, right? Assuming that his length is 1. Now, if his length isn't 1, we just multiply him by his old length. Yeah, we multiply him by his old length. Yeah, but if he we'll get to like maybe a little bit more later. His y position is going to be what? So his y position was 0. No, wait, that makes sense. Yeah. So his new position is cos theta sine theta. Now, if he was not at 1, 0, let's say that he was at like 1, 1. Right, so he's here. 1, 1. If we rotate him 45 degrees, he's going to be like on the y-axis somewhere. So we can do the same thing where we like draw our new axes, rotate them along with him. And so in their perspective, he's going to be at 1, 1, which puts him on the y-axis at some length. So you can say, once again, we need to do like some sort of rotation here. But now it's like a little more complex, right? Because we have, we can't just use these cos and sine directly, but we know they're like related in some way, right? And so let me think about this. There's like some way to figure out the math here where essentially you just use these same cosine and sine and they're like scaled relative to where they were on the x-axis and y-axis. So let's think about this. We know he's going to end up on y. We know that his position is... Oh, yeah. So the world... Wait, right. Where this gets interesting is like we can define the world rotation as this guy. So we can also take his y position and say like, well, his old x value of 1, 0 is going to be cosine and sine, and his new y value is going to be relative to like this rotation here. So we do the same thing here where we do like our y position is now relative to this angle change here, if I remember correctly, something like this, which is still going to be 45 degrees. And so his new y is what? Let's think. I guess his new y is kind of relative to like this angle, I guess. Yeah. So here, if we were like at 1.0 on the y-axis, we go 1.0 over here. And so now we have the same thing where his new y position is... hold on, we can figure it out. 1 minus... Okay, well, we picked a bad angle here because 45 is going to be the same for both axes. But let's say it was like 30 degrees instead. So we'll just draw this. We'll redraw this. So we have like a small rotation like this, maybe. Boom, boom. Yeah. So his rotation of the x-axis, the new x10 is going to be the same thing, cos theta and sine theta. But the new one is the new y-axis location, like the one on the y, if he's here, is going to be at like, this is 1 minus theta, or sorry, pi minus theta. Pi over 2 minus theta. Yeah, there we go. Is like this angle here, because these two angles have to add up to 90. And so his position is going to be sine for y again, sine pi over 2 minus theta, and cosine pi over 2 minus theta or something. And these guys kind of like can be converted into these things called like rotation matrices. So you can like multiply these by x and y, and these will turn into like rotation matrix. Yeah. So we got the top side, right? Cosine and sine. And then I think that this turns into negative sine and cos, because I think that these guys get resolved that way. Like I think cosine pi over 2 minus theta turns into negative sine theta, if I remember correctly. And then you like multiply these by x and y. I didn't do a very good job of explaining this, but there's this like sick video by, what's her name? Rhea rotation matrix. This video here, when I saw this, I was like, I get it now. Obviously, I didn't get it enough to explain it well here, but all of this is just to say that you can define a rotation by adjusting your coordinate systems and then multiplying the new coordinate system by the old coordinate system, and then like you end up with your things rotated by that amount. So we can try rotating this plane around, instead of here, you can imagine our rotation that we were talking about before is like around some imaginary third axis. We can just define our rotations around our z-axis, and we should kind of see our square kind of like rotating this way. Yeah. So we can define our rotation matrix as a 2D matrix, and our x and y positions are like for each coordinate. Then you can like take your each coordinate x, y, and do like a matrix multiplication with these guys, so that you do like, this is like fancy notation to say like multiply x by this and y by this, and that's your new x. Multiply x by this and y by this, and that's your new y, essentially. So we can like huck our rotation matrix of our plane into our shader as like an input. That seems reasonable. So we can say like uniform, we'll do a 2D one for now, but we'll extend to 3D later. So like it's mat2 for a 2D matrix, and we'll just say like z rotation. And initially it'll be 0.0. And we can say, oh no, this initially won't have a value, I guess. I actually don't know how to set these, so maybe we'll give him an initial, we'll try to give him an initial thing, and we'll kind of see how that breaks down. I think it's mat2 with brackets like this. Let's see. OpenGL mat2. Mat2. So here you just define him directly like this. First column, second column. Okay. Yeah, so we can say our initial thing is going to be let's think. So we have sines and cosines. So we have like 1.0, 0.0, 0.0, 1.0 or something. That's our initial rotation, which also happens to be the notation for like identity, so this won't change anything. Which seems reasonable. You can get that with the constructor mat21. Oh, I see. Nice. So like they have a constructor that basically says diagonal matrix with 5 on the diagonal. Nice, 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 nice. Okay, and then we'll figure out how to update this later, so like by the rules of that like cosine sine rotation matrix. I guess maybe it would be nice to start with a 45-degree rotation. So let's see, like rotation matrix calculator. Can we just like throw a rotation here? Fuck. Fine, we'll do it manually. So we'll look at the rotation matrix Wikipedia. And we can maybe punch in here. Cosine, negative sine, sine, cosine. Yeah. Okay, so maybe we'll start with like a 45-degree rotation. So we can say cosine 45 point. Nope, this is going to be in radians almost certainly. So this is going to be pi over 4. I don't know if there's like a built-in constant for pi in GLSL. Oh, you can define it as radians 180, but they have maybe. All right. Well, you have to define it yourself, so we'll just define it for now. So here we're going to say m pi over 4 negative sine m pi over 4. And then we have, I think it was sine and positive cosine here. So sine and cosine. So if we do this, we should see our... if we take our positions and we multiply them by this matrix, we should see our guy rotated by 45 degrees and shows like a diamond instead of a square. So here we should be able to say like outvert times outvert is equal to z rotation times our current output vert. Cargo run. Unexpected square or closing parentheses because we had an extra comma there probably. Size mismatch for matrix multiplication. So we actually have to say that our out for xy is going to be the only thing that we're multiplying here because this is a 2D matrix. I think I left an extra character in there. So we can cargo run. There, okay, so sick. We see like a diamond now instead of a square, which is like indicating that our rotation is working. And we can maybe apply a rotation to that over time. So we could say, rotation degrees, maybe we'll say, is what our input is, and then we can construct our matrix ourselves here. So now I have to figure out how to like upload a matrix to OpenGL, which I don't know how to do right now. So OpenGL uniform mat. There's probably just some like function you can call to set it. GL uniform. What are we doing to set a value? We're saying GL uniform 1 F32, and so we can say like GL uniform matrix to F32 slice. That's a sick function name, but I bet you that's what we want, right? Like a 2x2 matrix of floats. Almost certainly. So this location, we're going to have to find the location of the z rotation. So we're going to do the same thing here where we look up the z rotation location. And here we are going to take in z rotation as the name. And we're going to stash that position here in our structure. So we only have to look it up once. And here we're going to do the same thing where we store that guy here, z rotation lock. Cool. And so here we should be able to say, I want to upload this something. We haven't actually defined what it is. We're going to put it in self.z self.z rotation location, and he has to be wrapped in a sum for some reason. And what we're going to upload is, I think he had other properties. He said something about like transpose, so we don't want to do any like fucking up of our matrix. And then we should be able to just say, here is our thing. So let's say if we upload 1, 0, 0, 1, that should go back to like ones along the diagonal, which do nothing. And we should see the square again. So we have to actually take this out for a second. Okay, so we're back to the square. And so now we can probably adjust this over time. So we'll go over here and we'll go to our main. And we will pass in a rotation that will adjust with the time as well. And I guess we can just say that it moves. We'll just say that the rotation is the camera position. And that will kind of automatically update at some rate. So let's say that our matrix now is, we're going to have to punch in cosine rotation degrees. We're just lying about what this input is, but that's okay. Then we had negative sine rotation degrees. I think we have to say that these are an F32 cosine and an F32 sine. Here we have F32 sine rotation degrees, and here we have F32 cosine rotation degrees. Okay. There we go. So we see him like spinning this way now as time progresses. Now, we can now just make a very, very, very slight tweak to this, where in our vertex shader, instead of applying this rotation along the z-axis, we can apply it around the y-axis. And we should see the rotation now happening. Yeah, look at that. He's definitely rotating in some way. Not what I expected, because we're probably not rotating him around the center of himself. But that's okay. Pretty sure that function takes values in column major order if it transpose isn't set. Oh, so maybe I have to set this guy to true to get the exact behavior that we expect. Like, that probably will just affect clockwise versus counterclockwise or something. This is going to swap the negative and positive of the sign. Oh, so maybe there's like a flip that's happening in there if we don't transpose. Sure. We can figure that out at some point. Okay, so what we'll notice here is that the rotation is actually being applied kind of relative to 0, 0, 0, if that makes sense. It's it's applied relative to the center of the world. So it would be nice to build up a concept of being able to translate an object in the world manually. But for now, I think... Oh, no, wait. Maybe this is right. That is kind of what we want right now. Because right now we have one plane is one face of the cube. And we just have to make sure that we apply this rotation before we do our perspective shifting. And so now we should get something that's like a little bit more what we expect. Yeah. So here he's like rotating around the center of his cube, but his cube only has one face on him. And then we're getting farther away as we move. So if we add on a second face now, we should be able to see that rotation happening. So let's do the same thing, but at positive z. Right? And we should now see two of them. But we don't because we're only drawing one of the two faces. So we have to draw 12 vertices now instead of 6. And yeah, now we kind of see what we were talking about before where he's rotating. It's kind of weird that the perspective is not being applied. Here we were scaling our z distance probably relative to his input z position, but we want to check the z position after we rotate. So we'll scale relative to the rotated z, and now hopefully when they're sideways, yeah, nice. When they're, you can kind of see that as he gets farther away, he gets smaller. Let's remove this like camera movement over time. So here we'll just fix our camera position at -1 for now, just so we can get like a better look at that. But here we can kind of see that our as he gets like the back one is kind of like smaller than the front one, which makes sense because the front one's closer to us. There's like some like weird alpha shit going on here. I'm gonna ignore that for now. But we have like kind of like built up a concept of 3D perspective and 3D perspective and like rotation. And I think eventually we're gonna have to build up a concept of there's a few things that are missing here, right? One is that like we can't translate anything in the world, which is going to be a problem for us, which we will address soon. And another one is that the like things in the back aren't really being drawn quite correctly. We're gonna have to fix that, and we're gonna have to like import objects and stuff. But I think this is a good place to take a break because this stuff is like pretty dense in my brain. It kind of like hurts to think about it for too long. So we're at an hour and a half. I think that's a good place to call it. I think maybe tomorrow we come back and we try kind of translating the cube around. We can kind of build up we've kind of built up this like 2D we've kind of built up like 2D rotation around one axis, but you can kind of like compose these in 3D with like a small tweak. But I think I want to take a break and come back at tomorrow. So I think I'm going to call it there. Does one of those rectangles show transparency? You've got me curious. Maybe I fucked that up in some way. So let's see what I drew for like, what is our 3D fragment shader? He's supposed to be always fully visible. So it could be that our like depth testing is not working correctly, or I've made a mistake. Let's say everything is fully visible. Oh, it's not transparency. It's depth. It's darker as it's closer. And then probably we're not handling depth testing correctly. So probably it's drawing the thing behind even when it shouldn't sometimes. That's why you only see the thing in the background one of the two rotations. Because it's like whichever thing it drew first is being drawn on top. Because we don't have like depth testing on. So it looks like one of them is transparent, but it's not. Okay, yeah, I'm gonna call it. Thanks for watching. If you liked what you saw, I stream most days at around like 1 or 2 o'clock Pacific time. I think tomorrow we're gonna come back and try to build up the concept of like translation and like more arbitrary rotations, stuff like that. Maybe texturing, depending on how far we get. If you miss stream, there's a YouTube link in the Twitch description where all VODs will eventually get uploaded. They are usually uploaded the same day. There's a GitHub linked in the Twitch description, which isn't really too relevant right now because this isn't like stuff that's being committed. This is kind of like scratch code for now. But where things that we're working on more long-term get like committed and uploaded. If you're watching on YouTube and you want to pop by, say hi on Twitch, there is a Twitch link in the YouTube description. Yeah, I think that's all there is to plug. Yeah, do I have VODs? Yeah, they're on YouTube in the Twitch description. There's a link. There should be a link to VODs. Yeah, thanks for watching. Catch you guys in the next one. Bye!